And then, of course, you remember leaving off here. We're talking about the delta G of the Gibbs energy, the free energy of solution for various ionic salts. And so down at the bottom is a good approximation for the Gibbs energy of atomic salts. And we talked about that you can figure it out using the reduction potentials from electrochemistry. Do you remember how those are found? Something that might be fun for you to do in a lab someday.
Yeah, I don't.
So you make your galvanic cell, you have an electrochemical cell, and you will have your electrodes, and you usually have a solution. It's like you'll have an electrode more. Now, your reduction potentials are going to have a standard hydrogen electrode, because then you want to know what happens at the other electrode, specifically, and the hydrogen electrode is taken to be 0.
Okay.
Okay, so it's like, let's say you have a compound with copper ions in solution. And then what you want is you have a copper electrode, and you want to start grabbing copper ions, reducing them, and causing a buildup of more copper on the electrode. Okay, so, and then that's where you start to get, like, how much electrical energy does it take to reduce those ions? Those are your standard reduction potentials.
Okay. What was it that the E0 means?
So that's your reduction potential. Your F is your Faraday constant, and Z is your number of moles of electrons. So I use lowercase z to make sure it's like, no, it's not atomic number this time. That's number of moles of electrons. Usually I would probably call it N sub E, but this textbook uses Z, so I'm like, well, let's stay consistent with the notation. Because, like if it was me, I would write something like, something like that. Because we all know N is moles.
Right.
But, this textbook uses Z, so we'll just do that. Now, here is a list of standard reduction potentials. So right here, you see your hydrogen electrode is your 0 point. And so, and that's going to be your division between your positive and your negative energies for actually reducing these, reducing these ions. And so you see, for example, it takes quite a bit of energy up here at the very top, quite a bit of energy to reduce fluorine. So you have to break it apart, and then you reduce it to its fluoride ion. But so you'll find these lists in every textbook. The back of this textbook has a list of them in there. You see here some of the equations are longer, but this is the reduction of lead. No, wait, hang on. It's not the reduction of lead. It is a reduction. See, this is what breaks to your brain. So lead is oxidized. No, it is a reduction of lead. How do you know that? So lead is reduced.
You want to find the oxidation numbers?
Yeah, so look over here. You notice how you have 2 oxygens at a -2 apiece? This is a lead 4. It's reduced to lead 2. So yeah, it is the reduction of lead.
For sure.
We'll get back in the swing of things here in a few minutes. But let's kind of think about, I don't know, let's look at chlorine. Where is it at? Chlorine 1.36. So here. Okay, so let's look at that reduction. And a lot of times these are gas phase. Okay, so this is the reaction that we're looking at. Now, can we figure out the Gibbs energy of the Gibbs energy? So, and what we're figuring out here is Gibbs energy of formation. So remember, just keep in mind these we can then plug in here, find the Gibbs energy of solution. So some of these ions they're not going to be on the table in the back of your book, so you have to figure out what they are. So if we want the Gibbs energy of formation, okay, so the Faraday constant will always stay the same. Now, look at that there. How many moles of electrons is that going to be?
Just the two.
The two. So -2. Your Faraday constant. $96,485 coulombs per mole. And then your standard reduction potential, 1.36 volts. So you get a Gibbs energy of formation of -262. Or 39.2 joules per mole, or -262.4 kilojoules per mole. Okay. Let's see. Move this up a bit. I also wanted to take a look at a second one. So let's look at the reduction of potassium. Yep. So here's the question. So one of the things we want to take note of is when we're using these, so like our Gibbs energy of formation. First off, based on looking at this here, the reduction of an already positive ion, you think that'll be in the positive regime of a standard reduction potentials or the negative? You think that'll be easier to do or harder to do?
Harder to do?
Reducing something that's already positive?
No, wait, no, that'll be easy.
So it'll be what regime
It'll
will
be
it be?
negative?
Negative. So if you look over here, you see your potassium is right here. Now, we know and that's going to be volts. Okay, now, usually in our chemical equations where we're dealing with these, and we're talking about potential energy of formation, are we usually talking about like solid potassium, or are we usually referring to potassium ions?
Potassium ions?
So how would I figure that out?
How would I figure that out?
Yeah, because I could do the Gibbs energy of formation for just standard potassium using this. What about potassium ions?
It's got to be like in a salt or something, or like
it does, but how do I get how do I use this standard standard reduction potential to get the energy, so the electrical energy needed to ionize potassium?
needed to ionize potassium.
Mm-hmm.
Do you have to use just like potassium then?
I do, and then what's on the other side of the arrow?
It's on the other side of
If it's the ionization of potassium.
I don't know.
What do you do with in an ionization? What do you do with the electrons?
What do I do with the electrons?
Yeah, what's happening to the electrons in an ionization?
You're adding electrons?
Nope.
You're taking them away?
I'm taking them off.
Oh my gosh.
Ionization is removing electrons.
Okay.
So if I start there, what does the other side of that equation look like for the ionization of potassium?
Would that be the K plus of the electron?
Which then is going to give us an electrical energy of what?
It'll be positive.
Mhm. And so then our Gibbs energy of formation And we need -1 because we only want an electron. Be 96,485. And then a positive 2.92 volts. And that's going to give, it'll eventually give you a -2, maybe 1.7 kilojoules per mole. I just wanted you, I want you to realize that you can use these reduction potentials the other way.
Okay.
So if you're looking at a chemical equation and you're trying to find the energetics of solution, well, it's usually potassium ions that are in solution. So you need to find the Gibbs energy of formation of the potassium ion, not just the neutral potassium.
Okay.
Work on this for a minute or two.
All right. So do I need to do it in half reactions, or do I just need to like?
No, let's try to use this here.
Yeah.
So you're trying to find the Gibbs energy of formation of let's see. So do your equation for breaking down sodium bromide into its ions in solution.
Yeah. Right.
Because like sodium bromide, you can see. So you have the Gibbs energy of formation for that. Break that apart. And so what do you need the Gibbs energies of formation for?
Both of the ions?
Yeah, now we go back up here. Your sodium is right here. But this one,
Okay, to go the opposite way.
no, you don't need to go the opposite way. But it's a little different.
Oh, because there's two?
Uh-huh.
Okay, okay. I can do that. I can do that.
And I want you to think about, because this does not work the same way as an enthalpy. Because if I was to change that equation to give me only one bromide on that right-hand side, what do I do to it?
You have to have the whole thing?
Yeah. So you're going to get 1/2 Br2, 1 electron, and 1 bromide. And then you notice that that electrode potential is 1.09 volts. Now, if this was enthalpy, what would you do to that enthalpy number?
Just double it?
Not double it.
Have it?
Have it.
Oh, yeah.
That would be enthalpy, though. But this is reduction potential. So add an electrode. How many bromines are being reduced at a time?
Are they doing the two at a time, or are they doing one at a time?
One at a time.
One at a time. And then they'll combine.
Yeah. And so that's just your balanced equation.
Okay.
But it's reducing one bromine at a time to a bromide. So what do you think happens to the electrode potential? No.
Wait, no, it stays
the same.
Okay.
Because it's one bromine at a time.
They just assume they assume you know that one.
Well, once you've been taught, yes.
Yeah.
But electrochemistry is its own thing.
Yeah.
This is all within the area of analytical chemistry. Which I was trying to think, there's so many different ways you could go for the future that you want. But since you really want to use like the fullness of chemistry in a biological setting, I'm almost wondering if analytical chemistry might not be the way to go for you.
For just like.
Well, because then you'd be able to use all of your biological knowledge and you'd have like all of the instrumentation of chemistry in the laboratory by combining analytical chemistry with your biology. I'm wondering if that just might be the way to go for you.
Sounds fun to me. I don't know.
Because I know when I was an undergrad, my analytical chemistry professor, he was an astrochemist. So he would get samples from NASA and he analyzed them. And, so.
That's cool.
Okay, so here you notice that you have So there, now you can see it. And you're using the products minus reactants setup for delta G of solution.
Yeah, right. So, okay. When I'm doing that, am I thinking like products versus reactants of this whole one, or am I doing
Of this whole one here.
the whole one there?
Yeah. So you're doing products minus reactants of that one. You have the Gibbs energy formation of the reactant.
Mhm.
You need the Gibbs energy of formation for the two products, which is your sodium ion and your bromide ion.
And do I just add them once I've
Yeah,
calculated
yeah.
them? Okay.
Because you see all your coefficients are ones.
Mhm.
So, but you have to calculate those two Gibbs energies of formation.
Okay, cool. I can do this. It's
And also pay attention to that sodium equation there.
the sodium equation.
Yeah, what do you have to do to it?
Flip it.
Flip it.
True.
And then we have another derivation coming up soon, and I'm going to show you some equations that the book hints at, but that once you know them, you can plug numbers into them to get some really valuable information. The textbooks don't use, a lot of textbooks usually don't show you these equations because they're a little more advanced than normal.
Heck yeah.
But there's no point to be in here if we're not going to push you to that next level.
Exactly. That's what I'm saying.
I keep forgetting the guy's name. It's another Russian name.
The Russian guy.
I need to learn Russian because a lot of my favorite scientists in history are Russian, and I want to read their work.
Do it. What's stopping you?
Time.
Yeah.
Time.
That reminds.
I already know the Cyrillic alphabet. I just don't know the language.
Yeah. You know.
Like I would love to read Mendeleev's original work while he was building the periodic table.
Oh yeah, that would be cool. I don't know, like there's pretty good translation softwares out there nowadays, but
Well,
it is
there
like
is.
different to do it yourself.
Yeah, but I think there's more of a connection if you can read a person in their own language.
Yeah, it's probably true.
I'll never forget the experience of, when I was at my last career, when I got pretty decent at Mexican and Central American Spanish.
Yep.
And I didn't call it Mexican and Central American Spanish until I tried to talk to someone from Spain.
Oh yeah.
And I couldn't understand a word they were saying.
True.
I was really shocked.
Well, I mean, they pronounce like everything differently.
Mhm.
Like I had in high school, our Spanish teacher was like from Mexico. That was her first language, was like
Mhm.
Mexican Spanish.
Mhm.
And she was like, I don't like speaking to Spain people because I just like they speak so weird.
I mean, that's the thing. We call it Spanish, but it really is its own language.
Yeah, right. It's just like heavily influenced by Spanish. I got like 23,
Or
the whole thing.
very close. Let's take a look at it. Okay, so I'm going to guess it might be a calculator thing.
Maybe.
I love languages. I was just never very good at them. I want to be like one of my undergrad professors in physics. He could speak fluent Japanese, he could read it, and he knew all three alphabets.
Yeah, that's sick.
So what we're using And of course, in these Gibbs energies of formation, I always put the phase, because if you remember looking at these tables, the phase makes a difference. Now, when I go through this, there's also nothing to say I didn't use my calculator wrong. Always remember, just because I get a different answer than you doesn't mean I use my calculator correctly.
We'll see. Don't worry, I will call you out.
Just like I told you at the beginning of the semester, we are now at the level where it's not just a matter of me pulling stuff out of my memory. Like this is some of the stuff you're learning this semester is at the graduate level.
Thank you.
So it's, you're now at the very top of the game.
Yes, working on it.
So now we looked to the table and we found that. And it had that reduction potential, but that's not helping us for our solvation of sodium bromide. What we need is the ionization of sodium. That's what we use for the Gibbs energy of formation of sodium. Now, let's look at the bromine. Okay, now we have this, that's very close, but we only need 1 mole of bromide. Now, keeping in mind that this electrode will reduce 1 bromine at a time, that means that we can also say plus E negative is 1 bromide for the same reduction potential. That's one of those little things as you're switching over regimes from one energy to another. These are one of the things you're going to have in your memory. Because this one I've seen get so many people on tests. They go, well, I have to have cut in half the electrode potential. Absolutely not. Okay, now Gibbs energy of formation of sodium. Okay, so we look back up, we see that it's 1 mole of electrons. Then we have the 96, 485 coulombs per mole. And then we have the positive 2.71 volts for the reduction. Oh, no, for the ionization of sodium. That will inevitably give us a negative 261.5 kilojoules per mole. Okay, so then we look at the Gibbs energy of formation for bromide. And what would be really nice is doing this electrochemistry work when you're in biochem, you're going to be way ahead of the curve.
Heck yeah. Okay, that was a calculator error on my fault. I pressed the wrong button. So I think I did wrong now.
Oh, okay.
I just had Faraday's constant wrong.
Yeah, sometimes with big numbers like that, I've noticed that I punch things in wrong, so I have to go back and look at them.
Yeah.
And so this one is going to be our 1.09 volts which is eventually going to give us a negative 105.2 kilojoules per mole. Now I'm going to take everything and plug it into this equation here. Delta G of solution. Okay, so everything is in kilojoules per mole. So we have a negative 261.5 plus a negative 105.2. And that's going to be a minus a negative 349. And so our Gibbs energy of solution is going to be should be about a negative 17.7 kilojoules per mole. I also like upper level classes because I could do my math without having to write the units over and over and over again, because you're at a level now you can chase your own units.
Truly, I'm keeping track. Yeah.
So now, me personally, I like doing this better than the Hess cycle.
Yeah.
I find this to be more straightforward, but it's really kind of up to you how you do it. The Hess cycle, you have to look up a lot of stuff, like, you know, what is the enthalpy for the I mean, and I guess if you're really trying to calculate enthalpies, it'd be better to use the Hess cycle, but sure. I just prefer things like this. All righty, so now we're going to be talking about the energetics of the dissolution of an ionic salt. Now here we see one of these equations that we're going to end up getting to. So, and what we're talking about, of course, is is taking either our cation or anion and putting it from the gas phase into solution. So that's going to be our Gibbs energy of hydration. And so here we have what's called, make sure I get people's names right. The Born equation. Because for some reason, I knew it was Born, but my brain was Bohr. Now I don't remember. Yeah, there's that guy's name. We're also going to be dealing with the Kapuscinski equation.
Kapuscinski, that's a good one.
Yeah. So a couple of things in here that you notice. Now, of course, your R, that's going to be the radius of your ion. Let's see. Pay attention there. You see your epsilon R? That's the relative permittivity of water.
Permittivity of water.
So your epsilon zero is, of course, your permittivity of a vacuum. And then everything else you should recognize.
Okay, yeah. The Z is still the same as the last thing. Yeah.
Cool. All right. Let's see. Okay, so the basic energetic setup that we're looking at here is, remember this. I thought I brought a diagram down. Yes, I did. There's diagrams up above. Gibbs energy of shear solvation. Now this we did earlier. Because you remember we were breaking apart you have to break apart the lattice, all that stuff. Now, but what we can say is that your lattice energy this allows us to actually find the Born equation. Your lattice energy is going to be the Gibbs energy in a vacuum. So, since we know that, let's start with an equation you should know. We'll start with, let's say we're in a vacuum, we start with some spherical point charge. And then, let's see. Now, this is where the joy of being a physicist comes in, where most of your pure chemists would go, absolutely not. But
yeah, I've done this before. Is that V or is that a new? No, that's
V.
Oh, it's B?
Yep.
Now I've seen this before. Of course I have. Might be.
Do you remember what it's called?
This.
For a spherical point charge in space.
It's the electric potential.
That's the electric potential.
Yeah.
So now we need to look at the work done. To Z times E, which is going to be the total charge on the sphere. Okay? So we remember our basic equation.
And we're just assuming it's atom stuff, so that's why we're using E.
Well, E is going to be E is your fundamental charge.
Right.
And so then it's just how many of those do you have?
Okay.
So Z is your number of moles of charge carriers, which is your electrons.
Right. And since we're doing atom stuff, that's why we're using
Mm-hmm.
All right.
Yep. So of course, remember work is V times Q, but in this case, we want to use the differential equation, V dq. And so then we can say, well, let's plug in the potential, and now we have Q that we can integrate over. The work done to charge the sphere up to the total charge of Z times E. Let's see. So we'll pull out all the constants, 4 pi epsilon 0 r, the radius of your ion. Our limits are 0 to ZE. Q dq. All right, Miss Calculus.
I can do this.
What is the solution of this integral?
The solution of this integral, it's got to be 1/2 Q squared.
It is 1/2 Q squared. This is your power rule.
Yeah, I can do that one.
So what we're going to get yeah, you're in Gregory's class. I need you to know how to do this one.
Yeah, I have no excuse. If I didn't know it, that'd be really disappointing.
Well, we would just mock you relentlessly until you learned it.
Yeah, that's okay.
Okay, which means that after we do this, we're going to get you get 1/2 ZE squared. And what you notice is we get, we're getting a value in joules. So That's going to be our free energy of our vacuum. And it's going to be, so the denominator is 8 pi epsilon 0 r of your ion. Z squared E squared. Okay, that's in your vacuum. Now, how does this change for a charged sphere in water? Let's start with our potential again. So we still know we have the 4 pi epsilon 0, the Q over the R. Can you think about how this might change?
You'll use not the permittivity in a vacuum, right?
Well, what if I wrote it this way?
Yeah, that makes sense, right?
It's so that's your absolute permittivity. What do you think absolute permittivity is? You've never seen this before, so I'm just kind of asking you to guess.
Absolute permittivity.
For this charged sphere in water.
Gosh, I don't know.
What it's going to be.
Oh, okay. So it's like epsilon 0 times whatever the solution or whatever.
Yep. Your relative permittivity of water.
Cool.
I guess that first one kind of looks like epsilon r, but it's sub r, but it's just epsilon times r. So, okay, now, of course, charge to ZE, we're again going to be using which of course you're going to get the same kind of result. So the work this time equals your delta G of solvation. And now we go back up and we remember what we were looking at was that in the first place. So we're going to take our solvation minus our vacuum. Okay, so we're going to have 8 pi epsilon 0 epsilon r for your ion, c squared e squared minus now it's a matter of factoring. Now, technically, you could leave it like this. The textbook kind of has another proportionality in there. So what we can say then is that that's actually going to be the negative. And so now we have everything in kilojoules. But we want everything in kilojoules per mole. How do we get that?
You just need to divide by mole.
Yeah, how do you do that?
Do you need molar mass or something?
What has units of 1 over moles?
I should really know that.
You should. It's been a few years, but what number has units of 1 over moles?
Avogadro's.
There you go.
Okay, there we go.
So,
My bad, my bad.
okay, so again, denominator is 8 pi, epsilon 0, the radius of your ion. Now it's Avogadro's number. C squared, E squared, then 1 minus 1 over epsilon sub r, which is your relative permittivity of water. And let's take a look.
Heck yeah,
Yep, that's a Born equation.
we did it. Yay.
So again, most of the time the math isn't that bad if you just start thinking about it.
Yeah.
It's just so often people are so averse to thinking about it. That one up there might be a fun one for you to play with.
Is that just set into the 2/3 power?
Nope, that is a wedge product.
A wedge product. What does that mean?
Well, you have to look it up and figure it out.
Okay.
So fun one to play with. It's a new type of notation you've never seen before, but that is a wedge product.
What class did they look at that for?
Not sure.
Right there?
Not sure.
Okay. I'll type it into my phone.
Okay, so we have the Born equation. Now, this will give us a good approximation. It doesn't yield the greatest results. We can get our thermodynamic numbers by setting your enthalpy of hydration for your protons to 0, protons in gaseous phase. Let's see, then use for so then you'll use this and you're going to look at energies compared to hydrogen halides to get your system of self-consistent hydration enthalpies. And you can also estimate. Yeah, see, hang on. One of those numbers is the protons. That proton up top set to 0 should be aqueous.
Okay.
Then down. Yeah, I just forgot to put aqueous. I'm like, I thought gas looked weird. It's like, no, it doesn't make sense. Usually it's aqueous that is 0.
All of them should be aqueous?
No, just
that one.
That makes more sense.
Okay.
Then your hydration of your gaseous protons is a negative 1091 kilojoules per mole.
Yeah.
Let's see. I'll double check. I made everything gas. I have a sneaking suspicion that one's also aqueous. I'll double check.
Okay.
But then you could go about finding your delta G's of hydration by using the standard thermodynamic law.
Okay.
You'll find that the numbers end up pretty close to each other. It's just this thermodynamic law is going to take more assumptions than the Born equation. I usually prefer to get an answer that's very close, but maybe not exactly accurate, but uses less assumptions. Because here's the thing, if I start getting numbers that are wildly off from each other, then I'm making assumptions for this thermodynamic equation that are wrong. And I'm not really sure why they're wrong or what I'm doing.
Sure.
Versus the Born equation where I have actual constants and numbers that I can know.
Yeah.
So in my opinion, getting much closer using this is better than assumptions using this, unless I know, for example, my enthalpies and my entropies.
Okay.
Rules to keep in mind. let's see, highly charged ions have more negative values of this. Okay. Highly charged ions have more negative values of delta H and delta S. Size dependence on delta H and delta S. So remember we talked about that. You're going to get stronger attractions with smaller ions due to higher charge density.
Sure, like fluorine.
Mm-hmm. The variation of your enthalpy, your hydration enthalpy outweighs your T delta S. Let's see, for monatomic ions are about the same size. Anions are more strongly hydrated than the cations. It's because they have more favorable interactions in solution.
Okay.
So just a couple of rules to think about when you're talking about solvating different salts. Let's see, we'll pick up here next time and just kind of keep plugging out this chapter. Let's see how close we are to there's your Kapuscinski equation.
Kapuscinski. It's a good spelling.
Uh-huh.
You said we're almost done with this chapter?
Yeah, so I want to see how far, so there's another derivation we'll do.
I remember that one.
Go into that a little bit, and then we'll finish the chapter with coordination complexes.
Okay, that's the thing you were talking about.
Yeah. So coordination numbers.
Okay.
So we'll start here next time.